my presentation just telling where I come from. My university name is Roma III, means Roma the third. We are the third university in Rome, but actually third because we are the youngest among the public university. But we are the largest, the second largest in the number of students. Something curiosity about the logo of Roma III. We have this logo that shows an arc and a pyramid. That is basically this arc that you see here in São Paulo entrance door, and this is the pyramid. And maybe not everybody knows that in Rome we have a real pyramid also working. I mean, it's a museum, but you can go inside. This was built at the time of Julius Caesar, and there was a rich guy. The name of the guy, I have to check, is Gaius Cassius Epulo, who was just a tribune of plebs, so just a rich person from a rich family. But at the time, you know, that Caesar invaded Egypt and there was the story with Cleopatra and so on, everybody in Rome wanted to wear like Egyptian and eat like Egyptian, and this guy decided to have a tomb like Egyptian. And since in Rome, nobody allowed him to build the pyramid inside the town of Rome, this guy was there to build the pyramid right at the door of Rome. So this is why the pyramid is very, very close to the entrance of the town. And from the story, you know, that you see the pyramid through the gate, you see the logo of Roma III. That's the story. But if you want to know more about my university, here there is a link, and you can just look at our university on YouTube. But let's now move to the science, to the scientific part. And my talk is multidimensional multiplexing. So we are discussing about multiplexing data actually in optical communication, but I would like to discuss something about why we should do. We are working in the area, we are now in the area actually of the zettabyte area, and the number of bytes that are exchanged, the growth of the internet traffic per month is estimated to be 278 exabytes. So just to give some number, I had to take this picture from an astronomic website that tell us how many zeros a zettabyte has. And just to give knowledge of what is an exabyte, people have estimated that if we can store all the words spoken by human beings from the beginning up to now, we can sum up more or less 5 exabytes. While the traffic we exchange is increasing per month of more than 200 exabytes. So basically, it's much more, we see and we share much more what we can actually say. But saying that, so it is true that we like to communicate, and actually everybody likes to communicate wireless. So having is a laptop or a mobile and just sharing videos on the social. But the thing is that this is just the top of an iceberg, because what we really need to communicate is an optical fiber. So maybe for students that are not well aware how is a communication system, we can say that, we can say that going from when I share my content, my text message with my friends, I transmit data from my mobile, wireless of course, to a small antenna, small cell, and then all the traffic is collected and transmitted from the cell, from the antenna, to the point of present aggregation. And this is transmitted through fiber. After that, the data is multiplexed and switched in the central office, and then we need basically a lot of fiber to connect all the buildings in Manhattan, let's say here. And then, of course, we need to connect Manhattan to Rome, so we need to pass fiber under the oceans. So you see here the fiber link in yellow all around the globe. So basically what we need to communicate is a fiber, is an optical fiber. All the transmission systems that we are using now are almost based on optical links. And the optical communication links are basically divided in 3 groups. If I connect San Francisco to New York, I use a core network that is also called a long haul, and instead the connection inside a single town are called the metro, and of course the network inside my university or Santa Barbara University is an access network that is called the LAN, local area network. This is also important to recall that now we have a lot of access network that connect the central office to our homes. Actually, these systems are increasing a lot. These are called optical access network, and Verizon, Google are installing a lot of fiber basically to connect our homes. So the fiber runs very close to our home and inside the town, just to the central office that you can see here. But of course, as I said before, we needed to connect also Europe with the States. So we need a lot of submarine cables, basically for what they call bandwidth hangers. You see here, there is one example of a shark that actually is eating an optical cable. So the traffic through the fiber is really increasing, and you see is increasing exponentially here, starting from 1980. And what we know now is that all the installed fiber are really not enough. So basically we have reached the physical limit of the single mode fiber, or SMF. So we need to do something extra. The first option is say, okay, so you can just install more fiber. And this basically is a solution, but it is not the solution, just because you have to consider the fact that the traffic, the internet traffic, especially the optical communication environment system, require a lot of energy, and basically the energy consumption is increasing basically linearly with the total internet traffic. This is an example taken from Japan, but it's true for all the countries. So we cannot really keep all the working system and increase the capacity just adding more fiber links. So what we should do? Before telling the future, let me tell you start from the past. The past, the history of optical fiber communication starts in 1980, when Charles Quenkao basically demonstrated that an optical fiber link of only 20 centimeters was able to reduce the loss of a copper cable. And that was the very first experiment that demonstrated that optical fiber are much better than copper cables. And that's why when Kao received in 2009 the Nobel Prize. Starting from that time, a lot of happened. The very first big innovation was in 1990 when they discovered that a single fiber can transmit not only single wavelength, but more wavelengths. So basically, just using the concept of, you see here, Kao when he was young, and you use the concept of sharing the more wavelength on the single fiber. And that's all the story began, because starting from that time, basically everybody was digging, taking away copper. So this is a very old central office, and they moved to optical fiber, as you see here. But the very first innovation we had when we can transmit more wavelengths in a single fiber. So we use what is called wavelength division multiplexing, or in telecom you can call it frequency division multiplexing. So transmitting simultaneously more wavelength channel inside the fiber. This came with the invention of optical amplifier, OE, where all the fiber could be amplified in one go. So basically we have in an optical link the same that you have in a radio broadcast, where different radio can transmit at the different frequency. That's more or less the same thing. After that innovation, basically they discovered that we can, instead of transmit a single byte, we can transmit a symbol. So basically using quadrature amplitude modulation, for instance. So they moved to what they called coherent transmission. And then we used also polarization. You know that a photon is an electromagnetic wave, so can have two different polarization states. So the electric field can oscillate in two orthogonal domains, and therefore you can use both. And finally, this is basically the innovation of the past 10 years. You can use a fiber with more core. So basically each core transmits a different channel, and you can also use a fiber with the different modes. So you can transmit different modes inside a single fiber. Each mode, of course, carries different information, different data. So summing up together, the photon, the light, have 5 physical domains that are the time, because you see you can transmit a pulse after the other, so in time, and the wavelength of frequency. You can transmit different frequency channel simultaneously, but you can have two polarization, two orthogonal polarization. You can use quadrature, I mean, you use amplitude and phase of the photon to transmit more data in a symbol. And finally, you can use the space. So you can use a spatial multiplexing. That means you use a fiber with more core or a fiber with different modes. The domains are only 5, but they are almost fully used. So what you can do now, basically the idea is, the trend is shown here. Basically every time we use here more all of the wavelengths, there this is the time domain, this is the wavelength domain. We use coding, we have space, but basically the trend is there, and basically we have saturated. And scientists expect that not very far we have the capacity crunch. So we have no more enough bandwidth on the optical links that can support our connectivity, let's say. So the idea that I am trying to illustrate here to do an efficient resource use. So basically mixing up the 5 domains to get some more possibility to transmit the data in a more flexible and efficient approach. So we start with the very first device that was invented in 1980, that is called the frequency multiplexer or the multiplexer, that basically is a device that is able to separate, to split the different wavelengths, in the different ports of a device, like a grating, diffractive grating that separates the different wavelengths. This works as a frequency multiplexer or demultiplexer, and it was invented in 1988 by Main Smith, and the name is arrayed waveguide grating router, or phased array. Basically, at each port of the device, we have a replica of the same transfer function. So if it divides the signal into different channels, each channel is transmitted at an AWG port. Okay, during the last 15 years, my research was mostly devoted to modify this device and to invent or give more application to the AWG, and to mix all the domains together. So mixing polarization with space, with switching, and so on. And let me start with another domain that we included. Of course, it's a virtual domain that is called the code. So how this device works? Basically, this device can separate the different wavelengths using this slab coupler that works as a two-lens system. I think that most of students that have attended the course of optics or photonics know that a lens performs the Fourier transform. So the second coupler of this device performs the Fourier transform. And since here we have a grating, so we sample the Fourier transform, what we get is the discrete Fourier transform. So with this modification, basically, we can use the device for orthogonally frequency division multiplexing, where we take the signal to transmit, apply the Fourier transform, so we have different sub-channels, and then they can be transmitted together. Alternatively, we are also able to shape the response, the frequency of NAWG, basically increasing the number of the arms or designing better the coupler and so on. As I was telling before, we introduced the new domain that is called the code. Maybe you are too young, I don't know, but the second generation of mobile communication was based on codes. It was called code division multiple access. So it was not time, not frequency, but an hybrid domain where you can give a code to different users and they can access to the network. We did the same in optics. But the very difficult part at the beginning, when we started our research, was the encoder and decoder, because I was collaborating with my Japanese colleagues. And at that time, to generate a code and to read the code, so to decode, to see which code I am transmitting, we need a different set of devices, one for each code. So basically the system was unfeasible, was not possible to implement. We invented, well, actually, I have the patent, but we invented this device that is multiple encoder-decoder that can generate and simultaneously a large number of codes. So here you see the pics of our devices fabricated in Japan. This device can fabricate up to 15 different codes at 15 ports. The nice part is that it works very easily, so it's fully passive, so you don't have to use amplifiers or modulators. And you send the pulse into the multiple code, and you see here the signal, the codes generated at the different ports. And if you want to just read the code, send the code inside the multiple encoder. So take one code, send to the same device, and you see that at the match port you see a peak, and all the other ports you see basically no signal. So reading which port you read the peak, basically you can recognize the code. So it is also important that we demonstrated that the peak is very high respected to the cross correlation. So you can basically recognize the code very well. And therefore, in 2006, we started a long set of experiments. These are the very first experiment. Here is a peak to show that optical communication is quite complicated. You need a lot of lab equipment. But in that case, we transmitted 12 users. Each user was transmitting at 10G. And then, of course, we use this system in the access, because in the access, it's very difficult to use the time domain because you don't know the distance over each building from the central office. Instead, giving a code is much more easy to do. And therefore, we use also mixing together the frequency and the code all together. So we demonstrated this hybrid system. We have a multiple encoder-decoder to generate 10 codes, and we used also 3 wavelengths in that experiment. Or the record experiment was 1 terabit, basically transmitting 5 wavelengths and 25 codes, each code transmitting 10G. So this was a really record experiment also because it was not performing in the lab, but was performing inside the test bed, so installed fiber between in Japan. And these are basically the equipment. I say it's very complicated system that was implemented. After we were able to write, to receive support from European Communion for within the 7th framework program, we succeeded in fabricating the first device, integrated device that was able to transmit 1 terabit per second. That was based on this AWG. And of course, mixing up the thing, we start to mix code and space. So we use this system with the where we can transmit, for instance, 4 codes and 2 modes. And we can use this system, for instance, in an access network to simplify and to make it much more flexible. It is also possible to design an AWG that performs both code multiplexing and mode multiplexing. I don't give all the design guideline, but it's basically is an intuitive approach. And basically you see here the same code, but two different modes at the different ports of the AWG. And this graph here summarizes our results over the past 15 years. We started from 100 gigabit transmission, and we succeed 1 terabit transmission using 8 wavelengths, each wavelength carrying 40 gigabit per second and using 2 polarization. These are all results related to optical co-division multiple access. Okay, if we take a look at the AWG, we can also demonstrate that this device can be used to generate modulation format like QIM. So it could be used like a QIM modulator. In this way, basically, we can design like a infinite response filter. And this is the peak of a QIM modulator. Basically, it needs only some phase shifters, and basically this system is much more simple than a conventional 16 QIM modulator that requires 4 Mach-Zehnder interferometer in parallel. Of course, we can also design the AWG to perform a phase shifting modulator, so using a different approach of the FIR filter. Or we can also use for a phased array switch. Basically, we can switch the input from to one of the output ports in a very simple way. Okay, so mixing again code and amplitude, we can basically generate codes not only in the optical domain using the multi-port encoder-decoder, but also in the electrical domain using a modulator. And this is why we use an hybrid electro-optical PON, because in general in a PON, when you assign a code to the user, the code is fixed, especially if it's an optical code. Instead, if you use an electrical code, basically you can change the code, basically controlling the system in the central of it. And that's why we demonstrated this hybrid system for codes and 4 optical codes and 4 electrical codes that can be worked simultaneously in the one system. Or we can mix frequency and polarization. If the waveguides in the AWG are polarization sensitive, so they transmit only transverse electric or transverse magnetic signal, basically you can have at the 8th port of the device these 2 channels that correspond to the same frequency bandwidth, but they have orthogonal polarization and so on. So in this way, basically you can transmit different signal, different wavelengths, but also 2 polarizations simultaneously, and they multiplex in a very simple way. Okay, so let me pass to the more recent research. The recent research was related to mixing up time and frequency. So in the frequency division multiplexing, we transmit different frequency channels in parallel, and we are able, of course, to receive, to demultiplex them. In the time division multiplexing, I transmit the channel sending 1 byte after the other, in time domain, of course, and then we need a very fast receiver to receive all the bytes. All the two systems have the pros and cons, of course. And there have been many different experiments for both optical frequency division multiplexing, so multiplexing channel in the frequency domain, and OTDM multiplexing channel in the time domain. So what we have designed is to use an hybrid domain between time and frequency that basically is hybrid, so is in the middle between two. Why we do that? I think that now there is a video. I don't know if you can see it. I hope so. If you don't see, so if you transmit all the channel like OFDM, you have a very high peak to average power ratio, and transmitting this signal into an optical fiber, you suffer for nonlinear effect. In fact, when the transmitted signal is you transmit a lot of signal all together, the peak is very high, and the nonlinear effect in the fiber basically create problems at the receiver. Instead, we decided to use a hybrid system between time and frequency. So the signal is distorted, but then is more robust to the nonlinear effect of the fiber. That's one reason. And so to do that, we use the fractional Fourier transform. The Fourier transform, we all know, make a 90-degree rotation between time and frequency. But if I stop in the middle between time and frequency, basically I am performing what is called the fractional Fourier transform. So I can rotate of any angle between time and frequency. In math, the expression that you have to calculate the fractional Fourier transform is much more complex. And also the signal you get is more complex. Going from a box signal, if you apply the Fourier transform, you obtain the sync signal. But if you stop in the middle, make the rotation not 90 degrees, but in the middle, you get a complex signal with a strange shape. You can use a fractional Fourier transform to doing OFDM because the channels are still orthogonal, and therefore the channel you see are chipped here, but still orthogonal, and so you can use a wavelength selective switch to generate this channel like we did in the first OFDM experiment. So at the transmitter, we do not rotate from time frequency, we rotate only halfway here of 45 degrees. And then we transmit the signal, and then at the receiver, we rotate back to go back at the same frequency domain. So this is the experiment. You see the measured spectra. This is the simulation spectra, and we have measured the transmission error free for all the 4 channels. And then we evaluated the same system over a test bed. And again, you see here the eye diagram quite open. So basically the system is working and is not affected by nonlinearities. The next step is to mix more things, to make things a little more complex, and to go from OFDM, where the channels are transmitted in parallel, using fractional Fourier transform, so making a rotation in between time and frequency, and then transform this signal in Nyquist-OTDM. So basically to transmit from parallel and to pass to OTDM. OTDM is orthogonal time division multiplexing, where the signal are basically orthogonal in time and no more in frequency. The concept is related to the time lens effect. We know that the lens perform the Fourier transform because we first multiply the signal by the transmission function of the lens, and then we make the convolution that is related to diffraction. We can do the same in time. So we can basically apply time lens, that is this multiplication in time, and then we use the convolution, that is a transmission through a dispersive media. So a Nyquist-OTDM system generates these functions that are orthogonal, but then if I transmit through a dispersion compensation, dispersion compensated fiber, basically these pulses become sync pulses and they are transmitted one after the other. So we go from frequency division multiplexing, where all the signal are multiplexes in parallel, to time division multiplexing, where the pulses are transmitted one after the other. So this is the experiment. You see the pulses that are very nice shape, and they are also very short in duration. And the nice thing also that the pulses are properly delayed. So you don't need to add extra delay, just the system transmits all the pulses one after the other. We can use a wavelength selected switch to perform the fractional Fourier transform, but we have also designed and implemented an EWG device that performs the fractional Fourier transform that you see here in this picture. The design is a little more complex, but still working very well. These are the pulses generated by the EWG devices, and these are the pulses measured after dispersion compensative fiber. You see the pulses here have 8.4 picosecond duration, so are very, very small, and they are orthogonal, they are Nyquist pulses. Okay, so the last thing is to mix up together and basically make a system where you can transmit your signal. Let the receiver decide if he wants to receive the signal in parallel using OFDM or in a serial way using Nyquist-OTDM. So basically this is the system. The transmitter remains the same here. And then you can decide to receive all the channel in parallel, so using OFDM, multiplexing in the frequency domain, or in the time domain, so multiplexing in time domain. So basically the first receiver is made by a wavelength selective switch that filters out the fourth channel. And so you can receive the fourth channel in this way. Alternatively, if you decide to choose OTDM, basically you just add to the receiver a compensative fiber and you see one pulse after the other. And basically this is the story I wanted to talk, and of course I need to thank, I don't know, I hope you see my colleagues from Osaka University, Tokyo Tech Institute, and TNT, and all the projects that helped me to support my research. Thank you. Thank you, Caroline.
Yeah, thank you. Yeah, there's a lot of complicated but very interesting ways of achieving the multiplexing. So I guess I wasn't too familiar with code multiplexing. Can you talk a little bit more about how the actual encoding and decoding works for that?
Okay. Okay. Let me stop the presentation. Going back. I'll go back to the encoding and coding in the optical domain. Basically, when I started this research, that was 15 years ago, the device available for encoding and decoding are shown here. Basically, for each code, you have a coupler and then a phase shifter and the combiner. And then you generate this code. Each rectangle here is a chip of the code with a different phase that is illustrated here. The system was very, very complex. There were some experiments, but only with the two codes. Together with my Japanese colleagues, we have fabricated the very first device, this one, that was able to generate 16 codes. So if you send the pulse here, basically you have a replica, 16 copies of the pulse, but each chip of the code have a different phase here. And they are orthogonal to each other. So if you select one code and send through the decoder, at the output you see a peak only at the matched port. At all the other ports, you see no signal. Using this device, basically, I have to say that I have published more than 100 papers on these experiments. It was really successful device. Because codes are an hybrid way to share resources that is no time and no frequency. So you can use together with wavelengths and also together with time division multiplexing. And as I showed after in my presentation, together also with phase and polarization. So you really can increase the traffic and give a more flexible way, because when you give a code to a user in the phone, you have no problem of synchronization any longer. And each user can have his own code and transmit his own traffic. That is very easy to implement. And also the important thing that was that the encoder-decoder was fully passive. So we did not use, so you can put it in the central office without any amplifier or phase shifter or modulator. So it was very fully passive. I don't know if I answer your question, Steven.
Yeah, so I think basically the way it works is there's a specific set of phase shifts that are passively encoded at the transmission side, and then they are kind of decoded at the receiver.
Yeah, yeah.
So how is the phase shift maintained across the fiber? Is I know.
Oh yeah, no. The phase shift is between the pulses. So the phase shift is between here and here. It's between the pulses. So it's kept along all the fiber. We have had experiment and test bed. So is intrinsic. So if all the codes, the phase shift between the pulses in the code is generated by the encoder and cannot be changed. Even if you transmit through dispersive fiber, of course, nonlinear effect, some can affect, but dispersion, no. All the linear effects do not affect the code orthogonality.
Yeah. But since this is based on phase shifting the pulses, I assume it would be difficult to kind of combine this with coherent detection at the same time as having code the different codes.
No, we have also mixed the coherent detection and the codes. For instance, here, let me see. Sorry, that I go quickly. Sorry. Okay, this is an hybrid system. You have the codes, optical codes, the one that I showed before with the same multiple encoder decoder, and you have you generate QPSK signal. So you can have together. It can be a coherent transmission. You can use code and coherent transmission as well. Okay, because you on each code you can transmit a symbol that can have any amplitude and phase.
Okay, yeah.
Okay.
Very interesting. I'll have to look at it more, trying to understand everything. So I guess most of these are based on using them in long haul applications, I assume.
Mm-hmm.
Which of these, or have any of these become more widely used in that application, or what's the sort of?
Okay, I think that now there is some interest, research interest in the system I show at the end of my presentation, the one related to time frequency multiplexing. This is because it's very flexible and basically you can switch from time to frequency. There are many different applications where this is important to have. And we have presented our result at OFC 2 years ago, I mean. I think this topic can still attract some interest. Now, basically, a lot of research, as you know, is devoted to space division multiplexing. And increasing basically the capacity, because this is a really thing. But still, we believe that the use of the flexible use of resources is also very important.
Yeah. Are there any other questions from the other attendees?
Thank you for your talk. I did have one, so I'm not exactly in this field, but I really appreciated your slides and your graphics because it made me able to follow along a bit. Do you anticipate, if this is mostly like long haul fiber stuff, that some of this technology will really be able to prevent people from having to lay more fiber soon?
Yeah. The need to lay more fiber, this is mandatory. There is, especially with the 5G and 6G, it's mandatory to lay more fiber. All the research, let's say the 80% of the research in optical communication now moves to space division multiplexing, so using multi-core fiber and multi-mode fiber. Because of course you use a single amplifier to amplify all the chords, and so you save energy in this way. But when you think about, the access, maybe you need more flexibility, because if you want to switch data from one user to the other, in general, you have to transform the signal from optical to electrical, and this is a lot of waste in energy. So if you can use, for instance, codes or using different multiplexing modalities, you can save energy in this way. So this research is not for increasing the capacity of the core fiber, because but instead to give more flexibility to the way that we can handle the fiber, the data. We can switch the data, or we can address data to one user instead of to another.
Great, thank you.
Thank you.
All right. Are there any final questions before we wrap the talk and thank our speaker?
Thank you for the presentation.
All right.
Okay.
Thank you.
Thank you.
Yeah, thank you for joining us today, Dr. Cincotti. And there's a lot of interesting material. I definitely want to look at some of the papers that you published and kind of.
Okay. I am very happy to share idea with students, and of course to send you my papers or presentation. So just you can contact to my email, and I am very happy to discuss with the students possible research or whatever.
All right. Well, thank you everybody who came, and thank you again.
Okay.
This the talk will be, we'll have it on our website within the next day or so. So
Thank you very much.
Yeah. All right. Thank you.
Bye bye.
Bye.
Thank you.
Bye.
Bye bye.